All right. Let me see if I can get anyone. You say, huh? No? Okay. No one fell for it. I should have. She did that on purpose. Man. All right, so guys, it's the same concept as before. 2 days ago, when we did this, we were integrating an infinite amount of cross sections. That's how we found volume. Do you remember that, Morales? So it's the same concept. We're going to integrate a common cross section. So what's the difference? The difference here is that I'm rotating about an axis, the x-axis or the y-axis. On Monday, when we come back, we'll rotate about a vertical line or another line. It doesn't have to be vertical, just a different line besides the x and y-axis. And if you want to be you want to do something really, really hard, then you rotate like on a diagonal or something. But right now, what is the AP test going to do, or what is any test going to do for the Cal 1 level? Rotate about the x-axis, y-axis, or some other line besides the x and y-axis, either vertical or horizontal. All right, so a solid revolution. So here we go. The region between the graph y equals 2 plus x cosine x, which is this graph right here, and the x-axis over the interval -2 to 2 is revolved about the x-axis to generate a solid. Find the volume of the solid. So you can see what's shaded in, and I'm rotating this around the x-axis. So put a little arrow like that, and so that means that you're imagining the x-axis to be like a spindle. See? So imagine the x-axis like a spindle, and you're rotating it. And I know it's two-dimensional, but try to see if we can visualize this as three-dimensional. So it's going to be coming out of the board. So first, let's reflect this. So let's see, point, that looks like there, so point, and then this point looks like, not quite 3, so at this 1, it's going to be like right there, and then that looks like 2, and then this looks like 1.5, and that looks like 3 there. Looks like, I guess if you wanted to know what x value it is, just type in the x value into this equation, and you can figure out what the y value is, right? So these are just approximates. I don't know if I did it perfect or not. Man, yeah, that's actually pretty good. I'm usually not a good drawer. And let's add the three-dimensional components. This is actually the best drawing I've done like all day today. So here's a three-dimensional component. All right, so this solid looks like what does it look like? It's like a base. But hold on, be careful. It's not a base. It looks like a base, but it's not hollow. It looks like a base, and you can't put flowers in there. It's just one solid piece. So we understand that, right? Okay. So I take this base here, and I need to find a common cross section. You kind of got the hint right here. So I don't know. Maybe imagine this is like bread in a shape of a base. And if I were to slice it, I'm going to take a knife. I'm going to slice it right here. So I slice it. So here's my knife, and I'm slicing it. I'll use violet or purple. Here's my slice. I'm cutting it right there. What shape is that? And don't yawn. Imagine this is a bread in the shape of a vase. I know, it's so weird. If I slice it right there, and I turn the vase, it's a circle. Does everyone see that? It doesn't matter where you cut it. Look, I can cut it right here, and it's gonna be a circle. It's gonna be a circle. That cross section is gonna be a circle. Do we see that? Of course, the circle has different radiuses depending on where I cut it. Probably the biggest one is going to be here, or I guess this one's the biggest one, right there, Pam. But all those slices, all of them are going to be circles all the time. Now, they don't call at the university. Oh, I guess they do. But your professor, who's going to be a lot more formal probably than me, is going to call it discs. They're discs. I just call it a circle. A disc is a circle, technically, right? All right, area of a circle. Pi r squared. So there it is. I go volume equals pi integral -2 to 2. That's -2. This one's 2. -2 to 2 of my radius squared. dx. I haven't put the radius in. How do I find the radius? It's this one right here in, what color do I want to use? I'm going to use red. It's this distance from the x-axis to the top of that curve. It's the distance from the x-axis to the top of that curve. Well, that curve is modeled by 2 plus x cosine x. Do you guys see that? So that's my radius, 2 plus x cosine x. And there it is, guys. We're going to use our calculator, and we're going to type it in. So take your calculator and go pi on the outside, math 9. You can have the pi on the inside if you want, but usually we have it on the outside. Negative 2 to 2. And then open up a parenthesis, and I already forgot, what was it? 2 plus x cosine x. 2 plus x cosine x. 2 plus x cosine x, close, square. Put an x and push enter. Bam! 52.4288. The more digits, the better. Well, for me, 52.4288. If you're scared, or if you are prone to making mistakes, maybe put the 2 plus x cosine x in y1. X plus 2x cosine x. And here we go. Second quit. And let's see, math 9. Oh, I forgot the pi. It's okay. I'll do the pi afterwards. Negative 2 to 2. And alpha trace y1. Remember, guys, I forgot the pi. Put an x. And I don't feel comfortable. I'll probably give you the right answer, but I don't feel comfortable putting times pi here. So I push enter. And then whenever it says answer, I push times and I push pi. And then, oh, where did I mess up? X plus 2x cosine x. Is that correct?
No, it was 2 plus x.
Oh, there it is. 2 plus x. And not that I've done this twice today. X cosine x. Okay, there. Let's try it again. All right, I'm going to scroll up. And then times pi. There it is. Is that what we got? Okay, there is. I do want to show you, if you get this question on Desmos, because it was a perfect negative. If you get this question on the AP exam or any exam and you have access to Desmos, Desmos does calculate it for you. If you me later on, and we'll talk to you guys about Desmos. All right, there it is, guys. Okay, before we start, most of you are in robotics. Actually, all of you are in robotics or sometime, right? Well, but you did it at one time. All right. Do you know when I say washer, not a washing machine, when I say washer, do you know what I'm talking about? Okay. A washer looks like this, like a donut. It's flat, and in the middle, it's open, and all this is taken up. That's a washer, right? Okay, if I want the area of the shaded region of the washer, so there's something called big R, and there's something called little r. This is my big R, and I use capital R for big R. And this is my little r. See how that's a smaller one? And I use little r for that one. So when I say big R, I'm talking about the capital one. When I say little r, I'm talking about the little one. Cool? I hope that most textbooks write it like this. But if they don't, if they say R1, R2, notice it's the same thing. And if I want the area of the shaded region, you would go pi, and then big R squared, because that's how you find the area of the big circle. And then you got to subtract the area of the little circle to find the area that's shaded. So minus pi little r squared. So big circle minus little circle gives you everything in red there. Do you guys see that? Okay, how do we feel so far? Notice that both, and look, I'm color coding it, guys. Notice that both terms have a pi in them. So I can factor out a pi, and then I can just do big R squared minus little r squared. Chop, color code this. Well, I color coded the top part because that was the most important thing, and now I'm just writing. Does that make sense? So this is how you find an area of a cross section. This is how you find area of a washer. Cool? Okay, so here we go. All right, let's do this freehand. So without a calculator, it says no calculator here. The region in the first quadrant enclosed by the y-axis and the graphs of y equals cosine x and y equals sine x is revolved about the x-axis to form a solid. Find its volume. Okay, so here's my x and y-axis. And cosine x and sine x. So here's cosine x. Here's sine x. And they intersect at pi over 4 comma square root of 2 over 2. Hopefully we're okay with that. What's up?
For the cosine x, I remember from pre-cal it would be like a whole.
Yeah, but I'm only drawing the region that where they both. Yeah, it's a sinusoid. This would go. See, and then the other one would go.
Okay.
You know what I mean?
You're only doing like the region.
Yes.
They intersect.
Yes.
Okay.
I didn't draw that cosine sine graph accurately because when cosine is 0, sine should be 1. And when sine is 1, cosine should be 0. But you guys knew what I mean. Are we still okay? All right. I'm rotating this about what axis? The x or the y? I underlined it. Revolve about the. So rotate it like that. Put a little arrow like that on the x-axis. So, Chubb, I don't know how to rotate it. Well, first reflect it across the x-axis. Let's see. There it is. Not bad. Not bad. All right, here it is. Ready? Give it a three-dimensional shape. There it is. And this is, okay, remember guys, this is what's shaded when it's rotated. So this is like an empty, I guess the emptiness is shaped like a bowl, but remember there's still this part. So you can put your hand through here. Right? And then check it out. When I slice this, I'm going to slice it. Bam! I'm slicing it. What's the shape of that? It's a washer. Look at that. That's a washer, guys. And it doesn't matter where you slice it, it's always going to be a washer. I guess technically at the end here, you don't have a washer, you just have a blank circle. And at the end over here at 0, you have this technically. But besides that one slice and the other slice, they're all washers. Do you guys see that?
Okay. Oh, I know we're going to take like the integral
we are.
Actual washer.
We're going to integrate the washer. Volume equals pi on the outside. Integral. My lower limit is 0, and my upper limit is pi over 4. Open a parenthesis. It's big R minus little r. Big R squared minus little r squared. The big R, I'm looking at the washer. Maybe look at here to help you out. That washer is this washer. I'm looking at this big R here. The big R, the distance from the x-axis to the top of that curve. What will give me that distance always? What is that? 2 square root of 2. Well, what's the model? No, you're right. This is 2 square root of 2, or square root of 2 over 2. This is over here. Yeah, that's cosine x. You guys see that? So any x you choose, you can get your value of that radius by plugging in an x value into the cosine x. So my big R is modeled by cosine x. I'll put it here for good notes. Big R is modeled by cosine x. So I got to square it. Look what it says. R squared. So cosine x, and I'm going to square it. You put the square after the s, or you put the cosine x in parentheses, and then square it. All right. Now I'm going to subtract. I need to subtract little r and square it. The little r, the distance from the x-axis to the top of this curve here. What is this curve? Sine x. See how for any x value you can figure out what that length is, but because that's sine x. Do you see that? And I gotta square that because that's little r squared. Are we okay so far, guys? So minus sine squared of x. Close it, dx. Are we okay up to here? Okay. Could you do this without a calculator? Chubb, I don't know. There is no u. Yeah, maybe. Let's see. There is no u sub. You can't do u sub on this. Be careful. That's cosine squared plus sine squared. So let's see. Do you guys remember? So put this as a side note. No. I mean, you could, but then you'll have sine squared minus cosine squared. So, side note, do you remember that cosine 2x is equal to cosine squared x minus sine squared x? You can say no. Chav, I don't remember that. You don't remember that? Okay, do you remember this? Let's see what you do remember. This is all side notes. I'm gonna need more space. That's why I deleted it. Do you remember that cosine A plus B is equal to cosine A cosine B minus sine A sine B? Do you remember that? Okay, check it out. Guys, you do know this, and I know you know this. If I turn that B into an A, then look, cosine 2A is equal to cosine squared A minus sine squared A. Do you guys see that? So hence, from that, I can tell you that cosine 2x is going to equal cosine squared x minus sine squared x. And Gonzaga's over there like, yeah, I already know that because we did that earlier. Do you remember that, guys? So I can replace this cosine squared minus sine squared with cosine 2x. Volume equals pi integral 0 to pi over 4 cosine 2x, close it, dx. Now it's easy to do. So here's the pi. That pi is this pi. That pi is this pi. Bracket. Antiderivative of cosine is sine. Keep the argument 2x. If you were doing chain rule, you would do times 2. So I need to have a half here to get rid of that 2. And lower limit 0, upper limit pi over 4. And before I continue, anytime you could have done u sub. You could have with this antiderivative of that. U equals 2x, du equals 2 dx. Put in a 2, put a half on the outside. But guys, and in Cal 1 for this class, if you have a cosine or sine, if you have a trig, and you have a linear argument as the argument, a linear argument, whatever the coefficient is, take the reciprocal, put it on the outside. What's the reciprocal of 2? Half. Put it on the outside. You can always do that because of chain rule. So if it would have been 5x, you would have put a 1/5. If it would have been pi x, you would have put a 1 over pi. Cool? All right, here we go. I know, we're done. We're almost done. Upper minus lower, the half, both of them are going to have, both terms, chop. What do you mean by both? Upper minus lower, so factor out the half. So here it is. Pi over 2, bracket, sine, I'm going to plug in a pi over 4. That's going to turn into pi over 2. Sine of pi over 2 minus sine of 0. We need to know a little bit of pre-count, not much. Pi over 2, and what's sine of pi over 2? Not everyone at the same time. Sine of pi over 2 is 1, and sine of 0 is 0. 1 minus 0 is 1. 1 times pi over 2 is? So there's the answer. That's the answer for this one. Pi over 2. How do we feel, guys? Yeah, I'm not changing it. I'm not changing it, Morales. You guys okay? Okay, that's it. You guys already have the logic. Now we just got to practice a whole bunch. If the region enclosed by the y-axis, the line y equals 2, and the curve y equals square root of x is revolved about the y-axis, the volume of the solid is given by the definite integral 0 to 2 pi y squared dy. Justify your answer. So this is a true or false question. Is it true or false? Well, I don't know. Let's see. Hey, no, Yanni, that's the merit. Let's. I'm gonna sketch, and I'm gonna see if I can figure this. If we can figure this out. So here's my sketch. I know y equals square root of x just looks like this, and I know y equals 2 is just a horizontal line. So there it is. Touch. That. Remember, the y value is 2. So if the y value is 2, the x value has to be 4. Chop, how'd you figure that out? Well, look, 2 equals square root of x squared, x equals 4. I mean, you probably didn't have to do that. You can just probably just see it, but you know. Okay, are we still okay? All right. Notice, look what they told me. I'm revolving about what axis? Put a little spindle on the y-axis. I'm gonna continue to do this. I'm gonna extend it, and here it is. It's gonna look like this now.
Oh, so okay, so you're reflecting it, not rotating.
No, I'm rotating it. I just did a very bad job of rotating it. It's rotated. Kind of looks like one of those toys that you spin. It just doesn't have the little top curve.
Oh, it's like this.
Yeah, yeah.
Okay.
Rotating. Right. Look at the slice. Chop, how are you going to slice? I'm not going to slice with respect to x. Look, if I do a slice with respect to x, I don't know. What do I have there? It doesn't make any sense. So I'm doing it like this. Here's my slice. Bam. If I do that, my slice, it's a circle. Is that slice a dx or a dy? It's a dy. So that means I need my integral with respect to y. So, well, hold on. Let's find out. I'm going to square this. I'm going to square this. Oh, okay. Something's going to happen. Chop, do you see it? With more experience, you'll see it also. All right, check it out. Ready? My volume equals pi. So far it looks good. There's a pi on the inside. You can factor that out. Integral. My lower limit is 0. My upper limit is 2. Okay, so far it looks good. Let me take out this. Let me take out that line and that line. Okay, so far it looks good. We're looking good so far. My radius. I didn't do it. Okay, I suck at drawing, guys. Look, I got to be in art. Full disclosure, I already did. You know, I hate that I got to be in art. I didn't make my circle look perfect. But my radius is the distance from the y-axis to this curve. From the y-axis to that curve. That curve is modeled by x equals y squared. Do you guys see that? So my radius is y squared, and then I gotta square it because the area of a circle is pi r squared. So let me put it here just for good notes. My radius, I'm gonna write the word radius. The radius is y squared, right? Is the distance from the y-axis to this curve. Isn't that curve x equals y squared? I'm doing it in respect to y, so I have to put y squared instead of square root of x, right? Okay, so I put y squared, close it, and then remember, area of a circle is pi r squared, yes or no? So I gotta square that. Cool or not cool? Okay, if I square the square, y squared squared, that turns to what? Yep, y to the fourth, 0 to 2 of y to the fourth dy. True or false? False. And this is your justification.
Oh,
that's it. Hey, did you get sleep? Okay. All right. Are we ready for example 4, guys? Okay. Let R be the region in the first quadrant bounded by the graph y equals 8 minus x to the 3 half, the x-axis and the y-axis. Which of the following gives the best approximation of the volume of the solid generated when R is revolved about the x-axis? You have a calculator, so you could just type it into your calculator. I'm just going to go ahead and just see where it touches the x-axis. So 8 minus x to the 3 halves equals 0. Why did I do that? Where it touches the x-axis, right? Move the x to the 3 halves to the right. You have 8 equals x to the 3 halves. And then I'm trying to solve for x, so I'm going to put this in parentheses, I'm going to raise it to the 2/3. So remember, exponent raised to an exponent. You got to multiply those and make sure that it equals 1. So let's see what I get. Mirror, x equals the cube root. I think it's easier to do cube root. The cube root of 8 is 2, and now I'm going to square it. What's 2 squared? 4. So it probably looks something like this. Now, I'm not, I'm going to say I'm not an expert, but I would consider myself an expert in Cal. And here we go. But you should always have a growth mindset, guys. Be humble and always learn something. So I think this graph is going to look something like, here's 8, and it's not to scale. Here's 4. There it is. X-axis, y-axis, and the curve. So I'm looking at this region right here. Do you guys see that? Okay. I'm going to rotate this about the x-axis. So it's kind of looking like a dome, but on the side. I mean, not all domes look like that, but you guys see what I guess you could say flying saucer on the side or a pan or you guys know what I'm trying to say. All right, I'm gonna slice it. Chop. How's the slice gonna look? Well, it doesn't make any sense to slice it like this. So my slice, because look how I'm rotating. So my slice is gonna look like this. See, because that's how I'm rotating. So that's how my slice looks. What shape is that? It's a circle. That's dx. We're integrating with respect to x. That's a dx slice. See? All right, here we go. Volume equals pi integral. What's my lower limit? What's my upper limit? 0 to 4. Okay. And I just need my radius. The radius is the distance from the x-axis to the top of that curve. This one right here in burnt orange. X-axis to the top of that curve. What's that distance modeled by? 8 minus x to the 3 halves. Good job. Parenthesis, 8 minus x to the 3 halves. Close it. Put a square. Dx. Maybe they give you this one as a free response to do it by hand, and I think you could probably do it by hand. But right now we're just gonna just type into the calculator. All right, here we go. See, all those answers are in decimals, so probably just use your calculator. So I'm gonna put a pi, math 9, 0 all the way to what? Was it 4? Open parenthesis, 8 minus x to the 3 halves. And close it and put a square on it and put an X. Bam! 361.9. Is there one of those? And I actually don't like that they put one decimal, so I need to redo this. Put more decimals. Insert more decimals. Insert more decimals. 361.911. What's the answer? E. Cool. All right. Well, no, go ahead. Ask me. Ask me, Morales.
Is this because I was typing it?
Oh, okay. Well, we're good?
Yeah.
For sure? For sure?
For sure.
For sure. Okay. All right. Notice, I want you guys to observe. These answer choices all have, well, 3 of them at least. 2 of them. These 2 don't. These answer choices all have pi. So let's see if this one is something that's easy enough to do by hand. Let's see. All right. Let R be the region enclosed by the graph y equals x squared, the line x equals 4, and the x-axis. Okay. Because it said x equals 4 and the x-axis, we're only looking at quadrant 1. Because x squared touches the x-axis again at 0. So just draw quadrant 1. Let's see, what am I rotating in? Y-axis? I rotated with the Y. Yeah, quadrant 1 and 2. So exaggerate quadrant 1 and 2. So here it is, x squared. I'm going to exaggerate x squared just so I can have a pretty graph. And x equals 4. I'm going to call this line x equals 4. 4. Not to scale. And it says revolved about the y-axis. Put a little spindle or a little arrow indicating that you're spinning the y-axis, that the y-axis is like a spindle. And here it is. There it is. This is the region that I'm rotating. So that's what's filled in. Are we okay, guys? And if you want to give it some curvature so you can see it like more 3D, I guess it looks like this. You have, there it is. There's my curvature. So it's like an empty bowl. Like this part is empty. I know you're trying really hard not to write. This part is empty. And then it's not quite a bowl because I have like this and this. But this is definitely a bowl. And this will hold water. Cool or not cool? Why do you guys yawn with math class? But if we put a music video of like someone, you guys immediately get like, yeah. All right. But if I put on Bruno Mars, you guys are like, oh, okay, I'll stop. All right, here we go. You guys ready? Here's my slice. Bam. What shape is that? A washer. I overshot it a little bit. It's a washer. Is this a dx or a dy? dy. It's a dy.
Okay.
It's a dy. Bam, see? Yeah, look. Horizontal. dy.
Okay. So if it's x, it's like the same what we
If it's a vertical line, that's a dx, right? Change in x. See, if it's a horizontal slice, this is a thin slice. It doesn't really have the d. This really means like delta y, but dy means that it's practically zero because it's a slice. Do you guys see that? All right, perfect. We are on to something, guys. We're on to something. So we need this in terms of y. I need my integral in terms of y. Hey, we're almost done. We're almost done, fam. Relax. So here we go. I need to know the biggest this is. Well, if x is 4, this has to be 16. Chop, how do you know? Guys, this is y equals x squared. That point way over here, y is 4. So y has to be 16. And then look, it's curvature like that because I'm spinning it on the y-axis. There you go, yeah. All right, here we go. Y'all ready? Chavez ready. Volume equals pi integral. What's my lower limit? No. Nope.
What?
Respect to y.
Oh,
0 to 16. Lower limit 0, upper limit 16. Giant parenthesis. Big R.
Oh, yes.
It's a washer. Big R. Distance from the y-axis to way over here. Not one. This one's different. My big R is always 4. Do you guys see that? And I'll put it here for good notes. I'm going to write big R. I'm going to write big R is always 4. So you're going to write 4 and then put a square on it. Because remember, it was big R squared minus little r squared. I'm doing this. I'm doing this right here. I'm doing this right here. Big R squared minus little r squared. All right. What is minus? My little r. Well, the little r is the distance from the y-axis to this curve. But remember, here in terms of y. So right now I have, perfect. So right now, this is y equals x squared. I don't need that. Square root. X equals square root of y. Do you see that, Morales? So there it is. Minus the square root of y. Close it. Put a chop. How is that going to give us the radius of the little guy? Because it all depends on what x is, right? So if you're way out here, you plug in if you're way out here, the radius is 4 away from here to here. If you're here, like this guy tells me what the radius is. Yeah, I don't know why. So at the end of the day, it's you guys.
What?
Okay, are we okay with this? I didn't confuse anyone, did I? Okay. All right, here we go. Integral pi, integral 0 to 16. 4 squared is 16, so 16. And then the square root of y squared is just y. Oh, look. We can integrate that pretty easily. Pi. That pi is this pi. Bracket. Antiderivative of 16 is 16y, because I'm integrating with respect to y. And antiderivative of y is y squared over 2. Lower limit 0, upper limit 16. We're still okay. Do you know what 16 times 16 is?
130 something. No, 196.
Nope.
Oh.
No. All right, look. Right, 16 times 16. We don't have a calculator, right? 6 times 6, 36. Put a 6, put a 3. 1 times 6, 6. Add 3, 9. Put a 0 under the 6. 1 times 6 is 6. 1 times 1 is 1. Let's add them up. 6, 9 plus 6, 15. 1, 256. Do you see how we did that? Okay, 256. So here we go. I'm going to write pi. That pi is that pi. 256 minus, so we already know 16 times 16 is 256. 16 squared has to be 256. Dividing it by 2, 128. Oh, 128 is half of 256, so 256 minus 128 needs to be 128, and then times pi. Guys, you guys act like you guys are being tortured. Okay, we got one left. Perfect timing. Yeah, we got 4 minutes. Perfect. So don't worry. We'll be done. All right. No, we'll be done before that. Do you guys, it says, let R be the region enclosed by the graph y equals e to the negative x, y equals e to the x, and x equals 1. Do we know how these graphs look? We should. But if we don't, here it is. Y equals e to the x, looks like that. Y equals e to the negative x, so this is y equals e to the x. Y equals e to the negative x looks like this. And x equals 1 looks like this. Everyone knows the x equals 1, I hope. So the region that they're talking about is that triangular region kind of. Well, it's not triangular because it has curves. So non-Euclidean, maybe they call it that. But it's not a triangle, but it looks kind of like a triangle. Do you guys see that? Okay, let's rotate it. So, Chav, I don't know how it looks when you rotate it about the x-axis. That's why we're rotating it about the x-axis. It's going to look like this. Let's see. 1 and point. And it's not perfect, guys. I'm going kind of fast, but there it is. It's rotated, and if you want to see here, let me give it an image. There's my rotation. Do you guys see that? That looks actually really cool. That kind of looks like you can put your hand through here, maybe like a bracelet type of thing. You know, well, this has stuff on it, but you can put your hand through here. Well, probably this.
So it's circle.
No, the cross section is not a circle. Look, because remember, this is what has stuff. See? So when I do my cross section, bam, bam. I should have chosen a different color than blue. But yeah, it's a washer. Do you guys see that? It's always a washer. Cool or not cool? Not cool? Do we see it, Zamora Johnson? Do we see it, fam? Okay. Big R. So here it is. Big R. Big R is the distance from the x-axis to y equals e to the x. It's this in burnt orange. Do you guys see that? All right. That's big R. So that's going to be e to the x. Little r is the distance from the x-axis to this blue line. So this in purple. Don't worry, we'll be done real quick. So that's e to the negative x, little r. Do you guys see that? All right, here it is. Volume equals pi on the outside, integral from 0 to 1, giant parenthesis, little parenthesis, e to the x, close it, put a square on it. That's big R squared, minus, open parenthesis, e to the negative x, close it, put a square. That's little r squared, close the whole thing, put a dx. A little bit of algebra, not much. An exponent raised to an exponent. So this is e to the 2x, and that's e to the negative 2x. I just wanted you to choose the right integral. So pi, integral 0 to 1, e to the 2x minus e to the negative 2x dx. What's the answer? Does that make sense, guys? How do we feel? All right, we're done, guys. Good job.